Our next talk addresses the challenges of reasoning about resource usage at compile time. This talk will be presented by Di Wang and is entitled Liquid Resource Types. It is based on work developed by a team of researchers at the University of California at San Diego and at Carnegie Mellon University. The other authors of this paper include Tristan Noth, Adam Reynolds, Nadia Polyakova, and Jan Hoffman.
Hello, SFP and future viewers of this video. My name is Di, a PhD student at Carnegie Mellon University, and today I'm going to present our work on liquid resource types, a technique for automatically verifying the resource consumption of functional programs. This is a joint work with Tristan, Adam, Nadia from the University of San Diego, and Jan from Carnegie Mellon. Resource analysis studies the consumption of various kinds of resources in a program, such as time, memory, power, etc. One classic scenario of resource analysis is to find out the time complexity of algorithms. Resource analysis can also be applied to measure gas usage of smart contracts in blockchains, or detect side channel vulnerabilities in cryptographic code. In this talk, let's focus on a scenario about the time complexity of sorting algorithms. Consider a situation where we want to compare the performance of quicksort and insertion sort. These algorithms are functionally equivalent, and both of them run in quadratic time in the worst case. However, if we already know the input is nearly sorted, which means that most of the elements are in the correct place, which algorithm will have a better performance? In fact, insertion sort can achieve linear time complexity on nearly sorted data. So instead of a quadratic upper bound, how can we express a fine-grained time complexity of insertion sort? Look at the animation that might help you recall how insertion sort works. It goes through the elements in the list iteratively and tries to move them to correct places via swaps. Indeed, we can have a better estimation than the quadratic worst-case bound. The number of swaps is proportional to the number of out-of-order pairs in the list. Now, here comes a challenge that our work wants to address. How can a resource analysis formally describe and also automatically verify such a complex, value-dependent resource bounds? To achieve this, our work follows a line fork on liquid types, which support automatic verification of functional properties. For example, a function returns the absolute value of its input. Reason augments an existing liquid type system with a simple construct. Types can be annotated with potentials. For example, a list where each element carries 1 unit of potential. Potentials can be used to pay for the cost in the program. So if a function consumes all the potential in the list, the cost bound is linear in the length of the list. A major limitation of Reason's type system is that it only supports linear bounds. In our work, we proposed liquid resource types with the ability to express a lot more non-trivial resource bounds. A key idea is that the potentials can be inductively specified from the formation of data structures themselves, which allows us to express the time complexity of insertion sort. In general, liquid resource types provide a mechanism for expressing and verifying superlinear value-dependent resource bounds. We formalize and prove the type soundness with respect to a cost semantics. We also implement an automatic type checker for liquid resource types and evaluate it on a suite of challenging examples. Now I have talked about motivations for resource analysis and the main contributions of our work. Before diving into the technical details, I want to first introduce 2 important concepts that our system is built upon: liquid types and the potential method. Liquid types can be seen as a refinement type system, where types are annotated with logical predicates that can constrain the values. A refined type can be written as a subset. B is the base type of the value, and psi is the logical predicate. For example, natural numbers can be defined as a refined type with integers. The predicate can mention a special variable v, which reflects the value of the inhabitant. In addition, arrow types can be dependent, and the result type can be annotated with a predicate that references the argument. For example, the type showed on the slide specifies a function that returns a list whose length is 1 plus the length of the input list. The potential method for amortized analysis is a classic approach for algorithm analysis, which can be dated back to 1985. The high-level idea is to treat a program execution as a transition graph among program states, and each arc on the graph contains the actual transition cost between 2 states. To analyze the resource consumption, we devise a potential function phi that maps each program state to a non-negative number, such that the potential of the state is enough to pay for the actual cost of the current transition and the potential of the next state. In this way, the potential of the initial state provides an upper bound on the actual resource consumption. Our prior work, Reason, has combined liquid types with the potential method to automatically verify resource bounds of functional programs. The idea is to annotate types with potentials. The potential annotation and the logical predicates are in the same refinement language. The difference is that potential are numeric, but predicates are Boolean. The potential annotation then defines a potential function on the values of the annotated type. For example, the type on the slide describes a natural number carrying potential equal to 5 times of its value. Potential annotations can also be conditional. The type just showed on the slide describes a list of numbers, where each non-negative element carries 1 unit of potential. With this construct, Reason is able to express and verify value-dependent linear resource bounds. Take a look at the functional program on the slide. The insertion function, as a subroutine of insertion sort, inserts an element x to a proper place in the list XS. We use tick expressions, marked in blue, to specify a resource metric. In this program, we use ticks to count the number of recursive calls. Reason can verify a value-dependent linear resource bound shown on the slide. However, it cannot express a type for insertion sort because it can only distribute potential uniformly within a list, but insertion sort requires a mechanism to describe pairs of elements in the list. Okay, now I have introduced the two important building blocks of our work, liquid types and the potential method. Now we'll show how our work extends prior work with two powerful mechanisms and how to reduce type verification to constraint solving. Our first mechanism is inductive potentials. Rather than only put potential to elements in a data structure, we can specify potentials inductively from the formation of the data structure itself. The code on the slide shows the definition of QList, a variant of list types with quadratic potentials. Here, the Q constructor maintains that the tail of the list carries one more unit of potential in each element than the head, and the tail itself is again a QList. How does such a simple, constant potential annotation lead to an overall quadratic potential function? Well, let's do a calculation. Suppose a list L of elements v1, v2 through vn is of type QList, where the value of type T carries p units of potential. Then, for every element vi in the list, it carries p units of potential, and by the definition of QComs, it also indicates extra potential equal to the number of elements to the right of vi. Therefore, the obtained potential function is quadratic in the length of the list. More interestingly, we can use value-dependent inductive potentials to express fine-grained bounds. The type ISList shown on the slide is almost identical to the type QList, except that the extra potential required by the ISCons constructor is not a constant 1, but a conditional expression that evaluates to 1 if and only if the element in the tail is less than the head element. In other words, the potential specified by ISList is exactly the number of out-of-order pairs in the list. In this way, we formally express the fine-grained time complexity of insertion sort in our type system. However, inductive potentials on their own are difficult to use. The potential annotations are built into the data type definitions, so any slight change in the analysis or in the resource metric requires redefining a new data type. To address these issues, we have proposed a second mechanism. Abstract potentials. In liquid resource types, we allow data types to be parameterized by a numeric potential extractor. Thus, both QList and ISList can be seen as instantiations of a more general list type. The list type is parameterized by a numerical function Q, which takes two list elements as arguments. Then, in the const constructor, we use the function Q to define the amount of extra potential added to the tail. With this abstract type, QList can be defined as list with Q instantiated with a constant 1 function, while ISList can be defined as list with Q instantiated with a conditional expression that compares to elements. Now you may wonder, with this new construct, how can type checking in our type system be automated? Let's use the insertion sort program as an example to illustrate the reduction from type checking to constraint solving. The program uses insert to iteratively place elements to the right place. Our system does not infer types, so we assume that we have the type signature for recursive functions insert and sort. Our type checker goes through the program in a top-down manner and generates constraints on the fly. For the sort function, initially, the context only contains the argument xs. After the pattern match, if xs is an empty list, then it carries zero potential. But because it is also free to create a new empty list, the nil case is verified. Otherwise, if xs is not empty, then the potential of xs is transferred to the variables head and tail, the components of const constructor. Use the definition of cons, we can unfold the type signature and obtain the potential stored in head and in tail. Then in the rest of the program, there are two function calls. At this point, we need to split the potential in the context into two parts, and each part is used to pay for the cost of one function call. In the top-down phase, we don't really know how to split the potential, so we create symbolic potentials annotations and generate constraints among the symbols. Note that for the call to sort, it's wrapped by a tick expression, so we need to use the potential to pay for the tick. For simplicity, let's assume that the type checker uses the potential stored in head to pay for the tick. So in the context for type checking the call to sort, the annotation on head becomes p2 minus 1. Now let's take a look at the constraint generated by our type checker. The constraint asserts the existence of P1, P2, Q1, Q2. First of all, there are constraints specifying the potential split. The potential in different parts should sum up to the original potential in the context. Then, for the tick, we need to ensure that the potential is enough to pay for the cost, which means that the potential after the tick is still non-negative. Finally, the type checker generates constraints for function calls. For the call to sort, we assume that the type parameter A is instantiated with an unknown potential annotation S, which is used to thread some potential to be used by the later call to insert. Similarly, we use the signature of insert to generate a constraint on S. Now, after the type checker generates all the constraints, it tries to solve the constraints by finding proper instances of P1, P2, and Q1, Q2. These constraints are essentially second-order conditional linear arithmetic constraints, and solving such constraints automatically is a well-studied problem. So in this way, we obtain an automatic type checker for the liquid resource types. As for theoretical aspects, we formalize and prove the soundness of liquid resource types with respect to a cost-aware small-step operational semantics. Our soundness theorem ensures that a well-typed closed program will never run out of resources if it starts with an amount of resources equal to the initial potential specified by the types. Details of the theoretical result can be found in our paper and the technical report. After I explain how our type system formally expresses and automatically verifies resource bounds with liquid resource types, you might wonder whether the system is effective in practice or not. Let's first take a look at some reusable resource annotated data types, which we'll use to specify the type signatures for our benchmark programs. The first one for quadratic potential over list we have already shown during the presentation. The second one specifies exponential potential over list by doubling the potential in each element of the tail in the econst constructor. The third one defines binary trees. To capture tree height in the potential, the node constructor adds q more units of potential to the element in the subtree. So basically, an element at the leaf carries q times h units of potential, where h is the depth of the leaf. In this way, we can express a resource bound like O n log n if the binary tree is balanced. The fourth one also defines binary trees, but it assigns potential to a specific root-to-leaf path on the tree. This is achieved by parameterizing the type by a logical predicate as a guide to a specific leaf. With these data types, we are able to express and verify the time complexity of 12 challenging benchmark programs. As the table shows, the resource bound can be polynomial, non-polynomial, or value-dependent. Our prototype implementation is reasonably efficient, and no other automated resource analysis system can verify all of our benchmarks. Details of the benchmark programs can be found in our paper and the technical report. In summary, we proposed liquid resource types as an extension of liquid types to express and automatically verify value-dependent superlinear resource bound of functional programs. We formally prove the soundness of our type system and implement a prototype type checker that is shown to be effective in our experiments. Our work still has a bunch of limitations. For example, our system only supports inductively defined potentials, does not allow multivariate bounds like n times n, and we don't have a type inference algorithms yet. These limitations are interesting research directions, and we hope to explore some of them in the future. Thanks for your attention.
Thank you, Dee. At this point, if you're watching this stream live as an ICFP participant, please remember to look to see if there's a Q&A session available in your time band so that you can discuss this work with the author.